Cannon. I'm the Executive Director of Beyond Benign, a nonprofit dedicated to green chemistry education. The webinar series is designed to highlight relevant topics in green chemistry education for faculty and students who are looking to adopt green chemistry in their courses. And before we begin, just wanted to give you some technical information. We are broadcasting live and recording the session, so all attendees are in listen-only mode and all lines are muted. So if you have a question, then just please type it into the question box that you see right there on your control panel, and we'll have a look at them and we'll respond to as many questions as we can after this presentation. The recording will be posted on the link that you see on this page and also in the welcome box. And you can also see it directly on our YouTube channel, which you can subscribe to if you like as well. And any supporting documents, such as presentation slides, will also be posted on this link that you see here. For those of you participating in social media, please connect with us on Twitter or Facebook. We'd love to hear some live tweeting going on during our webinars, so please join in if you like. And a special shout out, we have a group joining us from the University of Colorado at Boulder, in partnership with the Chemistry Department and their Green Labs program, and this is being organized by graduate student John Malacha. And so thank you so much to that group for joining in and taking part in the discussion. And if there's any other groups out there that have joined and would like a shout out, feel free to use your chat or question box and type that in, and I'll send out a blast to the group. So the webinar is being brought to you as part of the Green Chemistry Commitment Program, which is a consortium program aimed at transforming chemistry education, expanding the community of green chemistry practitioners, growing departmental resources for those looking to adopt green chemistry, improving connections to industry, and affecting systemic change in chemistry education. The program is a voluntary, flexible program for adopting green chemistry student learning objectives and for promoting the work that you're already doing at your institution. You can find more information about it on our website, or you can email me directly. And as part of the webinar series, we give away a green chemistry resource, a book or guide or something like that at the conclusion of each webinar. So we're going to announce that randomly selected winner from our list of attendees. This week we do have a handbook of green analytical chemistry available. If you don't have it already, if you're the winner, you can choose that. So you'll receive an email from us right after the webinar requesting your contact information. So we'll get that right out to you. So with that, I'd like to introduce our speaker, Dr. Doug Raynie. Doug Raynie is an associate research professor at South Dakota State University. He joined South Dakota State in 2001 following 11 years in the corporate research division at Procter & Gamble. His research focuses on the use of supercritical fluids, ionic liquids, deep eutectics, and other novel solvents for biomass processing and analytical separations. Under his leadership, South Dakota State University has become one of the inaugural signatories to the Green Chemistry Commitment, where he serves on the advisory board. And this year, he received the ACS Committee on Environmental Improvements Award for incorporating sustainability into chemistry education. So I'm happy to turn the controls over here to Doug, who will be talking to us about green chemistry in the analytical course. So Doug, I'm going to make you the presenter. And can you see it, Doug?
No.
Okay. Let's figure that out. Okay, now let's try that again. Here we go.
Now, do you have my screen?
I think we've got you.
Okay, great.
Yeah, looks good.
Yes, so today, thank you, Amy. Today I'd like to talk to you about instructional resources for the teaching of green analytical chemistry, primarily, as Amy introduced, the traditional first year or quant course. However, before I do, I would like to put in a little bit of an advertisement. South Dakota State University, along with Northern State University and Black Hills State, all of them in South Dakota, have an RAU site in environmental and green chemistry. And I want to quickly show you our website. If you go to sdstate.edu, then over and from there go to the Chemistry and Biochemistry Department website, and over on the menu on the left you click on the REU site information. It describes our programs. It's a unique program. Northern and Black Hills State are both predominantly undergraduate institutions and separated by quite a distance out here in the Midwest. And so we've partnered with them in a unique program. And so you can see, for instance, we have research projects in environmental toxicology of nanomaterials, developing photoredox catalysts, drought tolerance, biofuel synthesis, photovoltaic materials, and I'm going to be doing some work in deep eutectic solvents. It says on here, and the reason I'm advertising this now is it says on here that our applications, review of applications, will begin February 1st and continue until positions are filled. We actually haven't started beginning the review process yet, so if you do have any students that are interested in spending 10 weeks with us this summer with a reasonable stipend, I encourage you to have them apply according to the application procedures shown here. And if they can do that as soon as possible, they would stand a much better chance of being selected. So with that, I would like to start off, first of all, by discussing some of the misconceptions, or what green analytical chemistry is not. And the first is I was involved in a project where some people wanted me to develop green analytical methods, and as I got into the project, really what they wanted was everything miniaturized. And yes, while miniaturization, we end up with smaller amounts of waste, we can't always minimize or go microscale and have the appropriate sample size. Yes, we're minimizing waste, but if we're still using the same toxic solvents, you know, we have to look at all of the 12 principles of green chemistry. Another misconception is if I eliminate the use of organic solvents, that means it's green. And again, yes, aqueous solvents are less toxic, but we do generate wastewater. The energy needed for solvent evaporation increases. So again, we have to consider all the 12 principles, not just toxicity or safety or waste generation. And the last one is very interesting. I'll be talking in a moment about a survey that Professor Peter Griffiths at the University of Idaho did in about 2007. He surveyed members of the Society of Western Analytical Professors, and I followed that up with an informal, an unsolicited email, and I asked these professors, 40 of them, do they teach green analytical chemistry? Should they? How would they? And this was, again, about 8 to 10 years ago when I did that. And at the time, green analytical chemistry was really just catching on. And what was surprising was exactly 100% either did not respond to my unsolicited email, or they said, I don't see the need. And in fact, the most positive response I got to my email was the type of response of, well, yeah, I guess I should, but I really can't figure out how to fit it into the curriculum. I really don't know that much about it. So hopefully the people that are listening to this seminar, webinar, are those that are interested in figuring out how we can fit it into the curriculum and how we can do that in such a way where we're enhancing the curriculum rather than taking something away. So first of all, I want to look at what is analytical chemistry and what is green chemistry, and therefore put together a description of what is green analytical chemistry. And I have always liked the definition of analytical chemistry that Herb Leitonen gave us 50 years ago, where he said that the analysis of a sample is not the true aim of analytical chemistry, but rather the purpose of our analysis is to solve a problem. and this problem solving is based on our knowledge of chemistry combined with our knowledge of making analytical measurements. Of course, I'm assuming that we're all familiar with the classic definition that Anastas and Warner gave us of green chemistry. And the part of that definition that I really like is that it's the use of a set of principles. So in other words, analytical chemistry and green chemistry are both, in a simplistic sense, merely ways of thinking about how we do chemistry. And so even though Cole gave us a definition of green analytical chemistry that he modeled after the definition of green chemistry, and if we read this definition, it's one of those definitions where it tries to be everything to everyone. I really think that green analytical chemistry is simply a marriage or a convergence of the two separate thought processes of doing analytical chemistry and doing green chemistry. If we'd like to get a quick assessment of the current state of the art of green analytical chemistry, just a few months ago in the November 30th, 2015 issue of Chemical and Engineering News, there was an article on greening the analytical lab, and it was primarily focused on corporate laboratories and specifically instrument development. But within that, they did discuss that at least 6 of the 12 principles are directly applicable to green chemistry and green analytical chemistry. I've already mentioned waste prevention, safer solvents, energy efficiency, reducing derivatives. Of course, analytical chemistry like to hold up the real-time analysis as that one is ours. That's purely analytical chemistry. And then finally, the inherently safer chemistry principle. At a minimum, those 6 all apply directly to green analytical chemistry. So I had mentioned Peter Griffith's survey of the Society of Western Analytical Professors. It was the results of the survey were published in Analytical and Bioanalytical Chemistry in 2008. And what the purpose of Peter's survey was to look at what topics were being covered in quant and I believe even instrumental analysis, but definitely in the quantitative analysis course. And some of these will directly apply to methods, analytical methods that are greener. And so one of these is the subject of sampling, which is only covered by about 50% of the schools for less than 1 lecture period. Statistics, as anybody who's taken quant recently knows, statistics are a big part of the course in most schools. The problem is the statistics being discussed are standard deviations, t-tests, f-tests, q-tests, things dealing with the analytical figures of merit, rather than the design of experiments, the chemometrics, the more advanced statistics that would be used for designing analytical methods and analytical schemes that are more green or environmentally friendly. Looking at specific techniques, one of the ways we can be green is to look at direct analysis. Most quant courses tend to be, in my opinion, very heavily weighted towards electroanalytical chemistry, and so direct analysis through, for instance, the use of ion selective electrodes is covered to a reasonable amount, but other direct analysis approaches such as reflectance spectroscopy, surface analysis likely are not covered. They were not surveyed in Peter's survey. Usually, if they're discussed at all in the undergraduate curriculum, they're shifted into the instrumental analysis course. Chromatography, while that may or may not be green, almost all analytical chemistry involves some type of separations. Surprisingly, covered by less than 2/3 or less than 3/4 of all schools, both GC and LC, and less than 1 lecture period each. Sample preparation, which is what I hold dear to my heart and is also the largest user, for instance, of solvents in an analytical procedure, was not part of Peters survey, looking at the books that are available for quantitative analysis, most schools will likely cover liquid extraction, but the newer techniques like SFE, solid phase extraction, solid phase microextraction, accelerated solvent extraction, and so forth, are probably not covered or briefly mentioned at best. And then the things that are related directly to the real-time analysis in the green chemistry principles, things like field analysis, process analysis, were not even, again, not even part of the SWAP survey and are most likely not covered by most schools. So what I would like to start with today is looking at a project I was involved with. One of the leading analytical quant books are the books by Dan Harris, either Exploring Chemical Analysis or his larger, more expanded book, Quantitative Chemical Analysis. And when these were undergoing revision in 2009, Dan's book is one of the few, if only one that I'm aware of, that has a laboratory manual associated with it. And so I was asked to review the book and the lab manual and make recommendations for how it could be made more green. And so one of the things I did was to add an experiment. I'm sure many of you are familiar with the experiment using liquid carbon dioxide to extract limonene out of citrus peels, where you throw your citrus peel into a polypropylene centrifuge tube, add dry ice, cap it, and put it in a plastic graduated cylinder full of warm water. As the CO2 liquefies, it will extract the essential oils, primarily limonene, and then the CO2 will leak out the cap. I had done this in instrumental analysis as a way to teach instrument development. I put it in the scenario that you're working for a food company, a flavor company, and you've read about this wonderful technique called supercritical fluid extraction. You want to give it a try. You think not only there are environmental benefits, but there might be other benefits for your company. But your boss says no. Show me that this works. And so how do you develop an instrument if you don't have one? And so we do this experiment and they write a memo to their boss and so forth. And I adopted that for Dan's survey. If you're not familiar with this experiment, it is widely published in the literature. I believe in the Journal of Chemical Education, but probably the easiest place to get a hold of it is the GEMS database that's run by the University of Oregon. It gives a lot of pointers and tips. They're actually the ones who developed this experiment because there are some safety concerns with this experiment. The other thing I did for Dan Harris's lab manual is, first of all, I wrote an introductory chapter, and in fact, if you want to know how introductory it is, it's listed as chapter 0. I'm not even chapter 1. But I presented this is what green chemistry is and my thoughts on what green analytical chemistry is. And then for the balance of the experiments, I took the greenness profile that was developed by Lawrence Keith, Liz Gruen, and Jennifer Young, and published in 2007, that was developed for the National Environmental Methods, or NEMI, database. I don't believe, I was just looking at this database yesterday, and if they still use this greenness profile, I don't see it on there, and maybe somebody can correct me. But this profile includes information or a green or not green on are the chemicals used persistent, bioaccumulative, or toxic? Are they toxic? And you'll notice some overlap there. Are they corrosive on either extreme of the pH scale? And do they generate more or less than 50 grams of waste? And so as this was presented and applied to the methods, analytical methods in the NEMI database, about half of the methods failed on chemical hazard. And as I looked at the experiments in the Harris lab manual, only about a quarter did. And I think that makes sense because most academic professors try and develop experiments where we're concerned about student health and safety. Waste, again, the 50 grams was just chosen arbitrarily in the greenness profile. About 2/3 of the NEMI database failed the waste criteria, and it was even worse in what we're using analytically in universities. For corrosion, about 20% failed in the NEMI database, and about 3/4 of them failed in the laboratory manual. And that makes sense to me because it seems like a lot of the experiments that we tend to do are based on manipulation of pH by addition of acids or acid-base titration, things like that. And then, again, a higher number of use of chemicals that are listed under the PBT. And if we look at this by experiment, we can see that there were only 5 out of, I can't remember how many experiments, probably 30 or 40. Only 5 of those experiments, including the carbon dioxide extraction that I added, were green in all 4 of those categories. On the other hand, 9 experiments, including gravimetric determination of iron, so a precipitation, iodometric titrations, thermogravimetric or electrogravimetric analysis, coulometric titration, a lot of variety of different methods failed the green profile in all 4 areas. Usually it was somewhere in between, so there was a capillary electrophoresis method that was green in everywhere except for the corrosivity measurement. There were 3 experiments that were green in everything except for the waste generation. A whole host that failed the corrosion and waste experiments, but were green in the persistence, bioaccumulative, and toxic categories, as well as the hazard or toxic category. And these, again, ranged from acid-base titrations all the way to amino acid analysis, ion chromatography of sulfur, and so forth. One technique was green in the corrosion category, but failed all the others. And so that's what I did for the Harris lab manual. And then along with that, as we presented this, I challenged the students in an introductory paragraph to evaluate the experiments in terms of why did this experiment fail the categories where it did, and what could you propose to do to make the experiments more green. So even though there wasn't anything in our lab manual that was specifically set out as this is green, but rather it was to encourage students to start to think about, are methods green, and what could I do to make them more green? If we're interested in those types of metrics, there's a number of them available with a whole host of intricacies. The NEMI database that I just showed is probably the most simple. There's another one that could easily be adapted into the academic laboratories, and this was developed by MERCK in their analytical division, Roy Helmy, Chris Welsh, and others, where they call it the analytical method volume intensity. And this is primarily designed for liquid chromatography waste generation, where they determine the total solvent consumption for both sample preparation and chromatography times the number of replicates, and divide that by the number of chromatographic peaks of interest. And the reason I like this is it's looking at solvents. That's all they're interested in, is solvent consumption or waste generation. But what I like about it is the fact that it's the only method that I'm aware of where it's coupling the green chemistry to some analytical metric. unfortunately, that metric is not something like accuracy or precision, but rather how many chromatographic peaks. And you can decide whether that's a good method of measurement of how good an analysis is. The other shortcoming of this technique is it doesn't distinguish between one solvent and another. But if you look at their paper that was published in Green Analytical Chemistry, it gives a whole series of examples using this particular HPLC method from a joint venture, and we don't have to try and identify these peaks, but if we look at their table and go through their derivation, they end up consuming, with their standard method using a 4.6 millimeter standard HPLC column, they use almost 1.7 liters of solvent, and it has an analytical method volume intensity value of 141, whatever that means, and you'll see relatively speaking what that means in just a moment. You'll notice by doing this, 70% of the use of organic solvents was through the HPLC step. So then they go through a number of examples where they use the smaller ID columns that give higher efficiency, and then they have to adjust their sample preparation extraction accordingly. And it ends up with using the lab on a chip approach to HPLC, where now they've used only 6 milliliters of solvent for an AMVI value that was started at 141 is now down to 0.6. So another green analytical method metric that could perhaps be adapted to the the analytical course. The one that we have used the last few years in our class is an assessment that we have developed very similar to the NEMI database profile, only we have found a way to include energy. We've defined health and safety and waste and environmental a little bit different so we can be more discriminating. We've come up with a symbol similar to this. At the time we were developing this, we weren't sure that Chrysler was still going to be using this symbol. But we do have the pentagon, and then each of the values have a red, yellow, green, or 1, 2, 3 scale, so it's a little more discriminating than the NEMI approach. We have a worksheet, and I'll give all of this derivation of this profile to Amy to post on her website. But there is a worksheet available so you can quickly look at, for instance, an SDS or the NFPA fire protection ratings, put them in accordingly, and develop the various ratings. And so to show how this works, these are 5 different EPA or USGS methods for the determination of polycyclic aromatic hydrocarbons in water. The first is, I believe, 550 is a GCFID, 610 is a GCMS, 525 is LCMS, and the last 2 are aminoassays. And you can observe from here that there is a little more discrimination between our method and the NEMI database. For instance, if you look at the NEMI database profile, that would tend to indicate that method 610 is more acceptable than the other chromatographic methods, but if you look at ours, that's not quite true. The F that we have on our safety scale indicates that the solvents used are flammable. You could also put in R for reactive or C for corrosive, etc. So the next thing I'd like to shift is away from getting the students to think about and evaluate the greenness of their analytical methods, and that is a lot of faculty, students, a lot of what we see in the literature are getting rid of toxic solvents. And you can find online, and it doesn't even have to be a professional literature search, but a simple Google search, you can find all types of evaluations and tables listing the green attributes of common organic solvents. GlaxoSmithKline, MERCK have those. The ACS Green Chemistry Institute Pharmaceutical Roundtable has one that is well developed. I particularly like this one by PFIZER because I like it because of its simplicity. They list not only the preferred solvents that are listed in green, they also list the bad solvents, the solvents to stay away from, listed in red or undesirable. And then they list the yellow or usable solvents that, yeah, you can use these if there's nothing else better. But what I really like about the PFIZER is not only are they suggesting to their medicinal chemistry group that these are the solvents that are preferred and undesired, but they also provide a table to list replacement solvents. So for instance, if you're currently using hexane, which is somewhat neurotoxic, they suggest using heptane. Another one that I find interesting is if you look at, if you're using chloroform, carbon tetrachloride, the preferred alternative is dichloromethane. But if we go back to their list of red solvents, dichloromethane is on there. So there are compromises that we have to make in life. And they do show that if you're using dichloromethane for extractions and chromatography, they do list some alternatives. And in fact, being somebody who is very interested in alternative solvents and green solvents of different types, if you get nothing else out of my webinar today, one of the take-homes should be, if you're using hexane in any procedure, try using heptane. If you're using methylene chloride, dichloromethane, especially in separations, try ethyl acetate. And I think that will go a long way towards greening up a lot of our separations, especially procedures. So lastly, moving away from solvents and into another alternative, and that is I want to challenge especially the faculty to be innovative in their thinking and be able to make connections. I was at a talk several years ago at the Green Chemistry and Engineering Conference, and there was a talk by a vendor that makes an alternative to EDTA. So first of all, I'll remind everybody that we use EDTA a lot in analytical chemistry for a variety of titrations of inorganic molecules, as well as anytime we need any type of chelant. And of course, it's a polyamino carboxylic acid. And of course, it's also used in mayonnaise, a variety of food products, laundry detergents, a number of other things. And even though EDTA does biodegrade, the problem is the rate at which society releases it into the environment exceeds the rate at which it biodegrades. So it is considered environmentally persistent. So this talk I went to at GCNE conference, the vendor was talking about their product, which was an isomer of EDTA known as ethylene diamine disuccinic acid, or EDDS. It has 3 stereoisomers, and one of them is readily biodegradable. And they were presenting this as an alternative to EDTA. As it turns out, I wanted to find out a little more information about this, and as I did some literature search, it turns out Procter & Gamble, the company I used to work for, actually already was using this in a lot of their laundry detergent products. So a lot of the people I knew at P&G had some of the information that I was looking for. So we were able to get a hold of a sample of this and use it in analytical titrations. So again, I want you to be aware of being able to make connections. Here's something used in the laundry industry or in other industries that we can adapt towards analytical. And so specifically, I'd like to look at the EPA method for water hardness determination. And so think of how often this method is done in water treatment plants and elsewhere. Of course, water hardness is a determination of calcium and magnesium, and the EPA method uses EDTA. It has this profile, so because EDTA is considered environmentally persistent, it has issues. We generate a lot of waste, and there is some corrosion because the sample needs to be buffered. One thing to note, if any of you have done this experiment, this titration, and that is it uses an areochrome black indicator. So it's not nearly as easy to see that indicator as it is with, for instance, phenolphthalein. I think areochrome black is the endpoint is something like dark blue to black or dark blue to darker blue. It's very hard for unskilled people to determine that, but yet we do at South Dakota State University. We do total water hardness by EDTA in our freshman chemistry laboratories, and that's part of what I'm going to show today. So I got this sample of EDTS and had 2 undergraduates working one summer in the lab, and they did the tap water determination of the water hardness using EDDS, and on a relative scale, they both got pretty close to 100% relative to what they got by the EDTA method. So we were very pleased with this. Again, the areochrome black was a very difficult endpoint, and these were undergraduates that did not have a tremendous amount of experience in titrations. So we went from tap water to look at the components. We made a standard solution of calcium, and we can see that we got pretty comparable results, accuracy compared to the known standard of calcium ion that we had created. We can see that in terms of precision, one analyst was quite a bit better than the other, but that's neither here nor there. However, when we turn to magnesium, we noticed that with EDDS, both analysts got quite high results, and we were kind of questioning that until we looked at other solutions, other standards, and as it turns out, and when we started working with a more experienced student in the laboratory, again, calcium ion works very well relative to the EDTA. Magnesium ion, we do have to make sure that we're buffered to a slightly basic pH, and we got slightly high but acceptable recoveries given the experience of the analysts for determining tap water. So then what we did is we turned this loose in our freshman chemistry laboratory. We did this one semester, so we had 20 sections of students, nearly 500 students use the standard EDTA, 9 sections, 56 student pairs do EDDS, and you'll notice that we got pretty comparable results, especially considering that, yes, they each did this in triplicate. Most of us used the first titration as kind of a range finding. Well, that was beyond what most of these students were willing to do, because we all know that the #1 goal of all freshman chemistry laboratory students is to get done with lab and get out of there as soon as possible. But given the difficulty of that titration, we were very, very pleased with this. And so now we're in the process of doing some isothermal titration calorimetry to determine the binding constants of EDDS compared to EDTA. We have looked at the EDDS for other divalent ions, manganese, zinc, lead, using UV-Vis. And once we get the isothermal calorimetry, titration calorimetry done, this paper will be submitted for publication. But a way of looking at things that are out there in the literature that aren't necessarily analytical, but thinking about how we can reapply them. So in conclusion, I just want to say that in my mind, there's nothing magic about doing green analytical chemistry, but rather analytical chemistry and green chemistry are merely ways of thinking about how we do chemistry and how we do our chemical experiments. So green analytical chemistry is the convergence of those two thought processes. And that's why I have constantly said that if you're doing analytical chemistry properly, it is inherently green. But hopefully today I've given you some examples of how we can go about greening the processes that we're teaching our analytical students. So with that, Amy, I'll turn it back over to you.
Thank you so much, Doug. That was a fantastic presentation and a good overview of how we can think about using green chemistry in analytical courses. So fantastic. So if you do have a question to ask, just type it right in on you'll see the question/chat box right there in your control panel on the right, so you can type that in. And while you're doing that, I can start with just a couple that have come in already. And also, I should also mention, sorry, I'm going to take back my screen here, which hopefully I can show you where to find all the supporting documents as well. And if you can't find something, just send me an email. So I'm happy to send you things directly as well. But one of the first questions we have is, what do you think the response would be today if you did another one of those surveys that you did? I think they're referring to the one where 100% didn't see the value in implementing green chemistry.
I think,
yeah.
Yes, I definitely think there would be some change. There's quite a few analytical chemists that are adopting green chemistry, and especially in the classroom. I already mentioned Liz Grahn down at Hendrix College in Arkansas. There's a whole host of others, and so I think it would be more widely accepted. I think if you look at the people that initially got involved in in green chemistry, if you look at the background of Paul Anastas, John Warner, if you look at the green chemistry workshop at the University of Oregon, they're all organic chemists. And so I think analytical chemists were slow to adopt green methods. That analytical chemistry, we're more of a service, and so people were willing to excuse our non-green methods. And so I think there's more of an awareness of that now. And I think the other thing is, if we look at all of the advances in analytical chemistry recently, and especially more instrumental analysis, but the HPLC methods using smaller ID columns, the more rapid ACE and extraction methods, they're all, even though they didn't necessarily set out to be green, they all just happen to be greener. So now it's a matter of us promoting them as green, as well as having their other attributes.
That's great. Okay, I've got a question that came in here. Does the EDDS formation constant data exist for other metal ions? I'd like to work on replacing EDTA in a codetermination.
Right now, we're determining it for calcium and magnesium. I don't know if it exists. I can't remember the literature. It probably does, given its use in industry. We want to make a direct comparison for our paper, so I suspect it's out there, but I can't say for certain.
Okay, great. And just really briefly, our winner is Stephen Thibersch. Sorry if I'm pronouncing your last name wrong. I know you're right up the street from us, so we can drive you over the book if you would like, right up there at Merrimack. So another question right here, is there another experiment you are working on now, freshman or other experiment? Anything that you have like a work in progress coming out?
Yes, my most recent research has been in deep eutectic solvents, which are a branch of ionic liquids. whether you use them analytically or as reaction media or whatever, they're very interesting to make. You take two solids, choline chloride, urea. It doesn't take even much mixing, and you get a liquid. They're really kind of cool, and that's one that we're looking at, developing some green analytical.
Great. That's fantastic. And I have two questions that came in that are addressing the cost side of some of these alternatives. One person's asking the relative cost of EDTA versus EDDS, and then and this one I think they complement each other, these questions. And how do you address the cost differences between in greener alternatives such as heptane, 2-methyl-THF, and and EDDS? Yeah, I guess that's a challenge.
The last I checked, and I'll have to admit that my EDDS was a sample given to us by the supplier, but the last I checked, their cost was comparable.
Okay.
But that's one thing to consider with calling things green analytical methods, is we still have to have the performance of the traditional method. We still have to have the detection limits, the sensitivity, and so forth, the cost. And if we don't have that, we can call it green all day, but people aren't going to adopt it unless we have the performance as well.
Right, absolutely. And we have some people just chiming in, yes, absolutely, they agree. And one final question, unless we get more in while I'm speaking here. In implementing green chemistry in your courses at South Dakota State, have you seen a reduction in the volume of waste, solvent use, or any other measurable benefits?
We've seen some reduction in solvent waste. However, that's really hard for us to measure because it's the analytical course is a blip compared to the freshman chemistry, the sophomore organic, as well as the fact that our curriculum, our number of students has grown quite a bit over the last several years. But I know we have seen some reductions in waste, and I think as we adopt greener methods across the curriculum, that will be even more greatly magnified.
Yeah. Well, that's fantastic. Well, I've got no more questions for you, and that was actually a really good set of questions that we had for you right there that came in. So thank you all so much for tuning in. A huge thank you to you, Doug, for giving this webinar. It's fantastic. Really got us to think about this. So thank you so much. And please have a look at our next webinar coming up. Dr. Sally Henry, who just published a lab manual for green chemistry in the general chemistry course last year, 2015. So she's going to be talking about that and how that applies in general chemistry and also in high school. And as always, you can find supporting documents by the end of the day today and recordings posted on our website there. And you can also just link directly to our YouTube channel if you like as well. So thank you so much, and look forward to talking to you next time.